So, you know, numerics are very important to help understanding things, but one has to be careful. For example, some things that in numerics cannot be done in let's say in a way reliable way is the formation of the shock. You know, as soon as the shock is formed, there is no problem. You can use the Rankine-Hugoniot condition, consider the shock as a discontinuity, and that works perfectly. But the problem is to form a shock, you know that there is as I explained to begin with, that you have a steepening of a gradient, and the final stage of this steepening cannot be analyzed numerically too simply because the characteristic length and time scale of the problem become microscopic. That is, scale of the molecule. So in that case, you have to do other things and different from the classical methods, which is used. Usually, there is a method that you increase artificially the viscosity in order to increase the length. But this is dangerous in a flame because, as you know, a flame is diffusion controlled. So this is, you know, create a shock created in a flame, very difficult to solve numerically, correctly. However, you have methods, and this method, for example, here, what did Hernandez, Sanchez, Raoul, you know, at one stage here, in order to resolve the very short time and length scale, he used this artificial way traditionally used by the numerician to solve shocks, and this is very dangerous because you are in a flame. So to make short a long story, you see, clearly there is a maximum here of pressure, numeric show, before to relaxing to the Chapman-Jouguet. This maximum, I cannot trust it. Okay, it's difficult. So we need the new methods. I don't know, very difficult. And this is not the first time that this is have been found by numericians. This overshoot above the Chapman-Jouguet detonation. Now, I want to discuss in few, let's shortly. Now, the problem that is often considered is a turbulent flame. Okay, I will discuss some few words after that to turbulence. But for the moment, let's say that consider that the regime of the flame you are considering is in a turbulent flame is laminar, wrinkle laminar flame in such a way that whatever be the reason for the wrinkling of the front, you still have locally a laminar front. This is called the wrinkle laminar, the wrinkle flame, turbulent wrinkle flame regime. What is a turbulent wrinkle flame regime? Once again, is when locally, at any time, at any point here on the front, the inner structure of the flame is still similar to the structure of the planar flame, except that it is curved, it is, but it is still laminar. Now, maybe I I should have presented first some few things about the turbulent flame. But you see now, if you consider the conservation of mass of this structure here is propagating faster, much faster than the laminar flame. Why? Simply because by conservation of mass, across each portion of surface of this flame, the mass flux is a laminar mass flux. So when you consider the total mass flux across this wrinkled structure, if you forget about that there are some local modification of the laminar flame structure, so it is simply the laminar flame structure multiplied by the ratio of the flame surface divided by the cross section of the tube. Okay, this is simply obtained by a conservation of mass. Okay, I am propagating for left to right. You see, you have a flame like that, and you look to this, and okay, this flame surface is going to move. It is not a constant shape, yes, but you have let's call S the surface. It depends on time, okay, fluctuate, but not so much in such a way that the mean of this S is well defined. And this, now, you have a mean, forget about the fluctuation, you have a mean surface, a mean surface area of the flame, and now you want to know what will be the propagation speed. Assumes that here you are at rest, for example, or behind. This has no importance. You want to know what is the turbulent, what is called a turbulent flame speed, which is an average speed of propagation of this structure here. So you just have to look to the conservation of mass. Here you are unburned, and here you have the burn. Okay? So if you now, as usual, what you do, is to sit on the flame. So you see this, the flow arriving with the velocity, the propagation velocity of the turbulent flame. Okay? And now, by conservation of mass, you see that the mass which is burned per unit time is simply rho u ut time s. You see? This is mass per unit volume. This is length square divided by the time. So this is a mass per unit time, which is consumed. And now, excuse me, stupid. The mass, excuse me, I am stupid. The mass which is consumed per unit time is simply time, the cross section here. This is the cross section. Okay? This is the mass, this is the definition of the turbulent flame speed. This is the cross section of the tube. This is the definition of the propagation velocity in a sense. turbulent propagation velocity. Now you can compute this by if you assume that each small portion of surface here or flame, the flame structure is laminar, the mass flux crossing this is delta is UL delta S, okay, rho U. Now, if you integrate on the surface, you have this S, and if you assume that the fluctuation, you neglect the fluctuation and look to the average, you have this. So you see that immediately the turbulent flame speed when you are in the wrinkled flame regime, which means that locally you have a laminar flame, is simply the ratio of the surface divided by the cross-section. Okay? This is a turbulent, what is called a turbulent flame speed. Now, to be back to my problem here, now if I look to on average, this is propagating at a speed which is larger than the laminar flame speed, okay, because this surface is much larger. So this can be large. Typically, one measure turbulent flame speed in a tube, let's say at least 10 divided by the laminar flame speed, let's say it's between 10 and 100, but 100 is more is something like that. Now, if you consider the tip here, if you assume that the tips are on average propagating with this strong velocity, this is not possible except because you are laminar here, except if you have a backflow. And in a sense, you see, you are in this situation similar as this one. You know, every tip here is pushed from behind by the burn gas flow, which is generated from the lateral part of the flame. You know, here you have lateral part. If assume that here, oh sorry, assume that you have here a closed wall. So now, if you have a closed wall, once you are going, so here there is the flow velocity is 0 behind the burn gas here, and this you should have a backflow acting on the tip, on each tip here. So in a sense, you are close to the problem of the laminar elongated flame that I have just described for you. You have it, except now that the problem is stochastic, that this is going to have fluctuation. This makes the life more difficult. But roughly speaking, this is the same. What I want to say is that when you have a transition now like that to detonation, it should be locally, typically the same as what I have described with my laminar flame, except that you have to consider a chaotic effect, which is not going to change drastically the nature of the transition, but that you cannot predict exactly where it's going to, is it going to appear here, here, here? You don't know because this is flapping back and forth. And so solution is not steady in a sense. But the fundamental problem, the transition should be similar. Now, what I have described here is quite different, from what was considered by John Lee in his book. For example, John Lee noticed the following, is that when you have a turbulent frame, whatever be the reason, because you have a turbulent flow, in fact, because the frame is going across obstacle and so there are turbulence, whatever. He said, okay, he noticed that this is going, so you have, you should find some, you are dealing with flame propagating around 100 meters per second, okay, and which is due to this surface extension, growth, and you see here I have plotted the Rankine-Hugoniot green curve with the reaction. This point is the initial point in the fresh mixture here. So an overdriven detonation is here, and you have a CG velocity here. Now, it is known by the same, constructing the same construction, but taking now the flame, not a detonation, but a flame. The flame is a decrease of pressure. The pressure is going, you know, the main difference between a flame and the detonation is look to the pressure. Does the pressure is larger in the burn gas than in the fresh mixture, or does it smaller? In a flame, it is smaller. In a detonation, it is larger. You see, here, this is the initial pressure, and here is the pressure behind the shock, okay? So, and the pressure behind the shock is not exactly the pressure at the end, but it's close. It is 1/2, not something like that. So you have an increase of the pressure. This is the pressure in the burn gas. Now, I did not put here, I did not draw here the Rankine, the Hugoniot condition for the shock. It's, I can show you. Okay, you know that. So now what noticed John Lee is that the flame propagation of this this is something half the propagation of the Chapman-Jouguet detonation. He noticed that. And then he transits to detonation. But just before transition, he noticed that the flow. And so he was thinking that what he has here, when the structure here should be, if, and this is a basic approximation, that this, you know, this construction on the plane pressure inverse of the density, for maybe I should give you the, remember, I should be back. Let me change to be sure that this is clear for you. So this 10, I have to go to 10. Where is 10? Okay. Supersonic shock wave. Okay, good. Okay. Rankine-Hugoniot, very good. Okay, now detonation, overdriven detonation. Here you have the picture, this picture. You know, this this is the Rankine-Hugoniot of the shock, and this in green is the Rankine-Hugoniot of the after heat release. So here is the initial point. Okay, I don't mind. This is the initial point. This is the Michelson-Rayleigh line. This is the state behind the shock here. Then you have a slight decrease of pressure, which is not written here, to go to this the burn gas here. Okay, and this is the end. This is and at the end you have the subsonic flow here. Exactly. But you see now, starting from here, because this green curve is still decreasing below this point, you can now consider the Rayleigh, the Michelson-Rayleigh line for deflagration, where which is smaller, the velocity is smaller than the is subsonic, much smaller than the supersonic, than the slope here. So this is, I cannot put the both of them. See, yes, I can do that maybe. Okay. Yes, you see. You see, this part here is this one. Now, the Hugoniot after heat release go below the initial point here. It go below, and now you can consider a Michelson-Rayleigh line like that, where now the pressure is decreasing. And this is a laminar flame. The problem that this construction is no longer useful in laminar flame because the pressure jump is negligible. But now, if you have a wrinkle flame, what did John Lee he was not the first one to do that, but to consider the structure that is called flame with using a Michelson-Rayleigh line, which is here, written here, okay? And this slope is smaller, so the flame velocity is much smaller, and you have a critical against flame velocity, which this has no meaning at all for a laminar flame, because a laminar flame never has a jump of pressure such large, because laminar flame is quasi-horizontal here. This is why this picture has no meaning for planar laminar flame. What some people try to do is to give an interpretation. This is what did John Lee. He say, okay, he notice what is noticing that this the average flame that he measured in turbulent flame was close to this CG, what he called a CG flame, just tangent. You know, you cannot. He noticed that, and in order of magnitude is right. So you know this gives you some flame velocity of typically 100 meters per second, something like that. It corresponds closely to the observation. And what he say, this flame should be unstable, and we should transit to detonation. So in his view, the transition for the detonation is a global phenomenon. But this is not the case, transition to the detonation is a local phenomena, quasi-instantaneous. Okay? And following this idea, people, good people doing good huge numerics for the explosion of star and so on, use that and develop the idea of John Lee and show that it is true that the transition occurs close to this point. So this, for me, has nothing to do with the transition from flame to detonation, at least in the laboratory frame. I don't believe a word about that. I still believe that the problem is local and is due to a backflow, as I have discussed in other. So this is, we see, the numericians are very, these works have been developed relatively recently. They make a lot of publicity with that, with very big numerics, flame everywhere and so on. But and they try to convince the reader that the problem is, as John Lee said, it is we go through a CG flame. In fact, it is not exactly what they see. They see something above the CG flame and then become unstable and transit to detonation. So I do not believe that. Okay, but because it is a global thing, nobody. I still believe in this, and in the experiments that I have described for you, the experiments that I've developed 10 years ago on the laminar flame speed, laminar flame, and so on, where there is a transition, at least the problem is clear in these experiments. Now, what is more important is that in most of the experiments of detonation, of flame, transition from flame to detonation, it turns out that sometimes, not all the time, because sometimes, as I told you, the transition occurs here, but sometimes the transition occurs in the boundary layer. That's the hotspot you see where the pressure there is a hotspot and that explodes. The starting point is in the boundary layer. This was observed long ago by Oppenheim, 65, 60 something. If you read the book of John Lee, excuse me, is excellent for that. He has a review of all the experiments, and this is an interesting book from this point of view. He said only a few things about the CG flame, very few things, very small lines, I am not sure he is convinced himself of the interest of this, but it's the dimension analysis that you can, the shock is there is a shock far away from the flame, okay, or what I call the lead shock. This is far away from the flame, but relatively to the shock, you have a flow which is beyond the lead shock, and the boundary layer develop behind in such a way that where the flame is somewhere here, you have a boundary layer where the flame is, okay, which is developed. The boundary layer here is 0 and develop like a boundary layer as I have described here. laminar boundary layer. So now if the boundary layer is turbulent, this is another story. But a laminar boundary layer, you can compute easily the temperature increase because of viscosity. You know, you have a shear flow here, and this shear flow, because of the viscosity, introduce here it is an increase. Where is the shear flow? It's not written. Yes, the shear flow. No. Where is the shear? It's not written. You can compute the viscous dissipation by the entropy. The entropy is something like 1/T, and it is like the square of the gradient. So if you compute that, you find out that in this, assuming that the boundary, that the walls are adiabatic, meaning that the wall, there is no cooling by the wall, which is not so bad because everything is very fast. So the transfer, the heat transfer at the boundary across the wall has no time. So you can consider roughly that the walls are adiabatic. In that case, you can compute easily order of magnitude the pressure, the temperature increase because of viscous dissipation. You see, when you have a shear flow, you increase the temperature. And it's easy to using the boundary layer and so on. It's easy to find that the maximum of increase of temperature you may have at the boundary is not so large. If you start with a temperature about, let's say, 300 K or something like Kelvin, you cannot go above 600 Kelvin. And this is too low to ignite a mixture, because I told you, you should be above the crossover temperature, which is about 1000 K. So this cannot explain by itself, this viscous effect cannot explain the transition, which is not most of the time, but they'll say time to time you see the hot spot where the detonation starts in the boundary layer. This is clearly seen experimentally. So it cannot be explained only by the viscous dissipation that increase the temperature. But now, if you, excuse me. Okay. Now, if you couple this increase with the compressional heating, because you have a compressional heating, which is coming that I have described before. Okay, here the temperature is increasing because of the compression of the unsteady compression of unsteady flow in the fresh mixture. So now, if you couple the compressional heating to the heating, viscous dissipation heating, you are going maybe. This is a guess. That is I think it's quite possible that you are created here a gradient at high temperature, and the Zeldovich gradient mechanism become possible. So there are no, excuse me. This interpretation has been given in a paper here that you have. This one, it's a numerical, based on numerical analysis, and the order of magnitude explaining that it is possible by order of magnitude analysis is in my book that you can find the order of magnitude showing that it is possible. And some numerics analysis, these are a paper written with Hélène Oran, who is a well-known numerical analysis in combustion, where they claim that to have seen that in the so this is another possibility and can explain the transition not at the tip as I have described, but in the boundary layer. Yes. And now, what about the trailing edge? Here in trailing edge, there is no backflow because you know the backflow are generated by this and go laser. Here there is no, you cannot have backflow because you do not have flame behind. So there is a possibility to have a transition of DDT. In that case, it has not been proved for the moment, but I can explain you how it can work. It's a quite different. For example, in order to understand that, this a beach, okay? This is the sea. This is the sand. The sand. These are wave, okay? This wave propagates are simply oscillations propagated with a given speed. This speed is can be computed simply. Now, what happens if the flame, if the waves are inclined? What is the velocity that you observe here? It is not, you know, the time to go from here to here is controlled, but now the distance that you propagate between the same time is much larger, okay, when you are inclined. So if you look to waves on the shore, as soon as the wave is not perpendicular to the shore, you will see a traveling wave much faster than the traveling wave that you see. This is simply a geometrical effect. Okay, keep that in mind. Now, if you consider the trailing, this edge is here, this and this, there is no backflow, but the tangential velocity of the apex here, the longitudinal velocity of this apex here, by a mechanism similar to the tilted flame on a shore, is faster than the laminar flame. So the tip, you know, in a sense, if you look in a steady state with the flow coming in here, this is a Bunsen burner. So the velocity of the flow of the Bunsen burner is higher than the laminar flame speed. This is why the Bunsen burner is conic. Okay, this is the reason. Now, now it is clear that if you look to the propagation of this trailing edge relative to the gas in front of the flame, if in front in the fresh mixture, this is much faster than the laminar flame speed, independently of the average, average flame position propagating. So for this effect. So now, what can happen is that here the velocity of the flames that are here, this part of flame that are here, relative to the gas, can be close to the sound speed. And in that case, you have a heat release which could be in phase, on phase, excuse me, could be on phase, the pressure increase because of the sound speed could be in phase with the heat release. And this is can be produced thermo-acoustic induced DDT. So this has for the moment, I did not see any experiments clearly showing that you can have a hot spot on the trailing edge. I did not see any experiment. What I saw is some numerics that describe this possibility of a thermo-acoustic induced DDT. And you have a recent paper here that I have mentioned that were doing numerics for simulating two flames with a tip like that, and showing that the velocity could be as fast as the sound speed. And this, in that case, if the heat release is in phase with the pressure, because now you may have a detonation. So this is only, but I leave these things open, and I say simply that much more works remain to be performed on all this topic. You know, the hotspot produced in the boundary layer, and the transition of detonation with a hotspot occurring on the trailing edge of a wrinkle flame. This was also observed by in a numerics, let's say, maybe 8, but I did not mention this paper. There was a paper with Sivashinsky and someone else who did numerics and find out a transition on the trailing edge. But no, there is no experimental evidence for that. But the experimental evidence is sometime, and not time to time, the hotspot develop in the boundary layer. And this, in that case, the theory I gave to you cannot work. It works only when the transition occurs outside the boundary layer. Okay, this is the only thing I want to talk about detonation, and now I have to make a decision and I need your advice. There are many topics that are listed in my contents that I do not have. What do you think about? For example, there is the thermo-acoustic instability. I did not talk about that. I can give you a brief overview of that. Are you interested in that? Thermo-acoustic instability? Yes? Yes? Okay. There are the turbulent flame theory. Who is interested in turbulent flame theory? The problem. The problem is that I am not an expert in turbulence theory. But okay, I will try to cover these two things. No, there is another one interesting that I can also, is the instability of detonation, galloping detonation. Do you have, people are interested in galloping detonation? One? Yes, it is related to spinning, but I will just, if I present something, it's only in the planar case, where this oscillation in the shock and the zone of heat release that pulsating. This is a natural instability. And then you have the cellular detonation too. But I have to, I cannot present the cellular detonation because I have to present first the galloping detonation, and then I have to describe in detail. Are people interested in the dynamics of shock, pure shock? No. Okay. So I cannot. So I will not describe the cellular detonation. So let's start with the thermo-acoustic instability, for example. A very short overview. You will see this is simple, and okay. So escape. Okay, so we are going to lecture 8. Now you understand why I skip the lecture, is to have time enough to talk about detonation. Aha. Okay. So I apologize because I did not prepare my talk, so I am going to And there are two different names. They are called thermo-acoustic instability, and what is well known also and studied, well studied in the laboratory, is what is called the vibratory flames. I say vibratory. Who knows the English better than I? How do you spell that? I don't know. Okay. All right. So let me start with the basics, the foundation of the problem. This was developed by Rayleigh in the 19th century, end of the 19th century. I will not go into the details of but I want also to give you some flavor of this vibratory instability of flame, because this is a spectacular experiment in lab and very instructive, you know. So Rayleigh was considering. Rayleigh tried to understand why the combustion in a cavity is unsteady, typically unsteady, and with strong oscillation, and that sometimes, and this is in fact the mechanism, this kind of instability that you have in rocket engine, that are the nightmare of the engineer. So in order to understand this, you start with ideal gas, P proportional rho T, and the coefficient you have here is simply the difference of specific heat per unit mass, specific heat at pressure, which is larger than specific heat at volume. Do you know where is come from the fact that the specific heat at constant pressure is larger than specific heat at constant volume? Why is it? It is that. Yes. Yes. In fact, Cp minus Cv positive is a constraint coming from the irreversible mechanics. That is related to what you say, but I will not explain that now. It's easy to understand that, because you know it's essential, because if Cp was not larger than Cv, you should have a negative pressure effect. So this will be dramatic. Okay, so Cp is larger. Now you take the Lagrangian derivative here, and you divide by Cp sur Cv, and you obtain this. And now you introduce simply the speed of sound as assuming that it is isentropic, so that that the speed of sound. Excuse me, I have a problem with my glasses. Right. Okay. So the speed of sound is the variation of the pressure with the density at constant entropy, and this is simply, you know, Cp over Cv, Cp minus Cvt. This is gamma minus 1 t. So you put that in this equation, okay? So you have this relation here, and then you you used the energy conservation, and from this relation that you obtain from the ideal gas law plus the definition of the speed of sound, and you couple that with the conservation of energy. You remember Cp dt, dp over dt, etc. And you you put that together. You eliminate the temperature here, it's easy, and you end up with a relation linking the derivative with respect of the time Lagrangian pressure to the derivative with respect to the time of the density time the sound speed equal to the rate of heat release per unit volume. So if you, for a short notation, you call this quantity, which is associated with the transfer of energy, either coming from the chemical reaction, or, but I will not take into account this, coming from the fact that you have a heat gradient of thermal gradient, you end up with this simple equation that relates the pressure derivative with the density derivative, introducing the sound speed and the heat release, because the pressure is an energy per unit volume. So it's an energy per unit volume and time. This is an energy per unit volume and per time. Okay, here you have this equation, and now this is a general equation, which is there is no problem. Now what you do is you consider small fluctuations. You have a vessel, you have this burning, and you consider a small fluctuation. So the overline are the unperturbed state, and the dot, not the dot, the prime are the fluctuation. They are small compared to the overlying quantities. A simplification also occurs when you consider that the mean velocity that you may have in your vessel, for example, in a rocket and so on, is smaller than the speed of sound. This simplifies a little bit. So in that case, you can neglect the convective term U grad in front of the acoustic term of the in terms of A grad. Okay, so this is a conservation of mass. This is a conservation of momentum. I have forget about dissipation, viscous dissipation for the moment. But if you now linearize this, you have on the left coming from here, you neglect this term, so that the Lagrangian derivative are a simple time derivative. And in that case, you have you obtain that the derivative of the perturbation of the density is simply related to the divergence of the velocity, the perturbation of the flow velocity. And thanks to Euler equation, you have that the divergence, the derivative of the flow velocity is related to the gradient of the fluctuation of the pressure. This is a linearized Euler equation. Now you assume that the unperturbed sound speed specificates are constant, to simplify. This is not very important. And you take this equation here that I have just derived for you, and you now eliminate the density from this equation from here, and you obtain, you know, if you eliminate, you take the second derivative, you have here, you obtain, wait a minute, where is it? Yes, because you take the second derivative, you have here the divergence of this is Laplacian of P, you obtain this, you eliminate now this density, and you obtain simply that the pressure satisfies this equation, which is a wave equation, usually D'Alembert equation. It is called either D'Alembert equation or wave equation. You know, if this is 0, this tells you that the second derivative of the fluctuation of the pressure is equal to the Laplacian of the pressure field, the fluctuation of the pressure field. And now you have a source term. And this source term is coming from the heat release. Okay? So this is the equation obtained by Rayleigh. And this equation is very useful also if you consider the noise generated by a heat source in free space. For example, it could be a flame anchored to a Bunsen burn, a turbulent flame. So you have a fluctuation of the heat release at one point, and you want to know what is the sound emitted from this source. And this is, I skip the detail, but you have just to use the Green's retard propagator, which is a solution of the D'Alembert equation with a point source delta function in space and time. This is called the Green's retard propagation. And with this Green retard propagation, you obtain that immediately that in spherical geometry, that the fluctuation of the pressure at a given radius, at a given time, is related to the second derivative in time of the heat release, integrate on the space, on the small volume in which the heat is released. This is called omega. This is the rate of heat release. It is a second derivative in time divided by the radius multiplied by a square, And this is shifted by the propagation of speed. So this equation is going to give you, this equation that I have written here, I did that on purpose because with this equation, you may easily study the sounds generated by an unsteady combustion. For example, in rocket engine or in ramjet or even in the okay, I do not have the vocabulary to say that. Now, you have, unstudied release is going to generate acoustic waves. Okay, that's I explain you the general mechanism of that. This general mechanism. So, and now there is a retroaction on this acoustic in a tube, for example, on the rate of its release. And for this, a famous experiment in the 19th century beginning called the singing flame is when you put a burner in a tube, you may depending on the position of the flame inside the tube, you generate the sound of the tube, and this was used to develop an org, but it never worked very well because it is not very stable. But this is a very spectacular phenomena called singing flames. And this singing flame mechanism was famous in the 19th century when the light was developed by gas flames. And these gas flames, there are a lot of stories of the noise made by this gas lamp. And there is a very interesting comment in the review Nature saying that to show how to prove how the sound reacts on the flame, they said that in a concert, the author see the flame of a lamp, of a gas lamp that follows the violin. This is you have this interesting paper in the Nature saying that this proves that there is an interaction between the two. The mechanism, excuse me, the fluctuation of heat at a point in the tube is related to what is known as Ritchie tube, where you have an hot wire in a tube. Depending on the position of this hot wire, it's just a wire that you warm up, for example, with an electric current. So it is red because it's warm. And then you notice the following: if there is a flow crossing on one side or the other, this wire, you have an exchange of heat because the flow is cold and the hot wire is hot. So when the flow cross this wire, the heat is released to the flow, okay? And it changes, And the quantity of heat which is released by the wire depend on the flow velocity. Okay? The transfer of heat between the two. But this now this shows you that there is a possibility to induce acoustic wave with that. Right? Because the transfer of heat is fluctuating with the velocity, so it is related to the acoustic wave. So you can create acoustic wave with this Ritschke tube. There is a full theory of Ritschke tube that has been developed not so long ago. You have a full theory of that. Now, in order to understand in simple words what is a thermo-acoustic instability, that is a coupling of unsteady heat release and acoustic wave, you look for the one-dimensional problem, for example, this one, or this one in one-dimensional, and you assume that the simplest retroaction mechanism that you consider is that the heat release is proportional, the rate of heat release, excuse me, the rate of heat release is proportional to the pressure fluctuation. But now, just by dimensional analysis, you know, a pressure is an energy per unit volume, heat release is an energy per unit volume, and the rate of an heat release is an energy per unit volume divided by the time. So when you have a proper mechanism where the rate of heat release is related to the pressure, you should introduce a time and a coefficient, a non-dimensional coefficient B. If you put that in one dimension in this analysis, and if you consider the Fourier, the space, the transform Fourier in space longitudinal of this pressure, the fluctuation of the pressure, and you call tilde pk the Fourier component of the wavelength, wave number k, inverse of the wavelength, this is component. You put this decomposition, because the problem is linear, you put this decomposition in this equation, and you obtain this. Now, this term you have the second derivative here, the heat release, which is proportional to B times this, is here, okay? Because you have delta P here, delta Q dq theta, you are here, and the Laplacian is here. So you obtain a very simple equation for each component of the Fourier transform, which is a second order differential equation, linear, with a first order term here. And if you do not have this term, what you have is simply the frequency, acoustic frequency. You know, when this term is out without coupling, what do you have? This is just the acoustic frequency, the acoustic modes. That this term and this term, when they are balanced, they tell you what is the square of the frequency. As you know, acoustic, it's a wave, is the sound speed times the wave number, or the sound speed divided by the wavelength. I don't remember. At what time did I start? I don't remember. I start at 10? No. Okay, so one has to, we need a break of 15 minutes. and me first.